Hello, my name is Chris Kopacz, and this is my final project for the Spring 2025 CSCI 104 Advanced Deep Learning course. The project title is Deep Purpose Drug Target Interaction with Binding DB. To begin, the motivation for this project is to explore a few different user-defined model architectures for drug target interaction and drug binding affinity score prediction through the use of the Python package DEEPPURPOSE. On top of trying a few different model architectures that are set up in the code, the external data source binding DB is also used. It is a very large data set that contains drug SMILE encodings as well as disease protein target encodings, FASTAs, and finally the affinity scores that are obtained through experimental results. After training and testing a few user-defined models, a pre-trained model that's available within DEEPPURPOSE is imported to compare the user-trained models to more canonical truth, or what you might expect from a well-trained model. Drug target interaction is important mainly because it helps cut down on research and experimentation costs. If you're able to take a drug and a disease protein with unknown interaction or unknown binding affinity, instead of setting up a drug sample, blind study, whatever's needed, this is a great first step to speed up that process and just check whether or not it's even worth continuing. Additionally, in the real world, oftentimes there are a number of cases where diseases are rare or they present with an atypical mutation, something that's not seen frequently. So data surrounding those specific use cases would be incredibly limited, and this offers a very cheap and fast solution to determine possible viable treatments for those diseases or conditions. And repurposing, as was shown in the homework during the semester, sometimes it might be difficult to gain the necessary authorization to test drugs for off-label purposes, and this provides a method to see whether drugs can be used for something that they weren't intended for and have a beneficial effect. DEEPPURPOSE is open source and built on PyTorch. Its benefits are that it's plug and play. All the model architectures are well defined. You just pick and choose which ones you want to use. The difficulty arises when establishing or defining the configuration details of those user-defined models. That was one of the cons that I ran into. The binding DB dataset is incredible. It is very, very large, so large in fact that loading the entire dataset caused my script to crash due to memory issues. So the models for this project were trained on a smaller sample set of the binding DB dataset. But the most valuable part of this dataset is that the labels are the output for supervised machine learning models like this are all experimentally generated. They're real world data, so they are true values that doctors or researchers know when they're training a model that whatever experiment they're conducting will be compared and assessed against actual data. It's not an AI imagination. These are the model architectures used. Um, the user-defined versions all employed a convolutional neural network for the target encoder. Um, During testing, this was just the simplest approach. I was having a lot of trouble with setting up the different configuration details. So keeping it simple on the target, the protein encoder, just made things a little bit more manageable. The drug encoding is where the variation occurs. We use Morgan, daylight, convolutional neural network plus recurrent neural network and a convolutional neural network to um, build the different versions of the drug smiles encodings. The pre-trained model is the MPNN plus CNN Davis model. Um, I had originally intended to include this model architecture as one of the user-defined versions, incorporating the MPNN architecture within DEEPPURPOSE. I found to be probably the single most memory-intensive component of the script, aside from loading the binding DB dataset. Every time I tried to run the MPNN uh, user-defined version of the model, it crashed by about the second epoch. As for the results, we'll actually step into the code here. The beginning of the notebook covers the installs, where the dataset can be downloaded. Um, DEEPPURPOSE actually provides an API. You can just type in code, whatever the function call is for loading the binding DB dataset. Again, because my assumption is because it's so large, I was actually running into issues loading it through the API. So I ended up having to download it manually and then just import a selected sample of that data set when running the code to keep the script from crashing. Here is a user-defined or cherry-picked subset of historical diseases, things like measles, typhus, cholera, diseases that have, in my opinion, been large problems for humanity. I was interested to see how well a pre-trained model evaluated these diseases, as well as if the user-defined models could get anywhere close to those results. All of the FASTA sequences were found on Uniprot, and the Uniprot codes are listed next to the disease names. This section of the code will load 100,000 records out of the approximately 3 million of the entire data set. It's set up in a way to be a random sample of the 3 million records. It won't just pull the first 100,000, it'll randomly select them. Then we have a helper function to put the data into a usable format. We further process the data and then step into the definitions of the model architectures. So on top of the memory issues presenting problems on their own with the data set being so large, the next biggest issue that I ran into was the configuration details for each of the user-defined models. DEEPPURPOSE does have an API or a function call. I believe it's called generate configs, something like that, where it will auto-generate configuration details. However, I found that it didn't always work. It sometimes left out certain details. Getting each of these right was a very intensive trial and error process to figure out which models required which configuration details in the keys in their dictionary, and which ones weren't needed. Overall, this was just the biggest headache in the project, but once it was sorted out, everything ran smoothly. Next is model training. Of the four models, Morgan plus CNN and Daylight plus CNN ran the fastest. I would say probably only about 5 minutes for the 100,000 records that were used for training. This is most likely because the drug encodings for Morgan and Daylight are the simplest representations available in the architectures. Each model was trained individually and not automated in a loop. This was done because if you trained all four of the models at the same time, one graph would be output at the end, and all four of the loss curves would be plotted at once, and they would all be blue. From my research, the only way that you could change the color of the loss curves, because this is an auto-generated plot by DEEPPURPOSE, the only way to change the color would be to step into the DEEPPURPOSE source code and change it there, and that's just not something that I want, not a task I wanted to take on for this project. So instead of putting all the training in a loop, I ended up training each model individually and generating its loss plot. So Morgan and Daylight were the two fastest. The two slowest were the CNN plus RNN, as well as just the simple CNN models. The one that included the recurrent neural network was by far the slowest. I think this took almost an hour, over an hour, to fully train. The CNN model was not nearly as long training as the recurrent neural network one, but still noticeably longer than the first two. It's also worth noting that all of the loss curves look fairly similar, and each of these spikes comes from when the validation split was evaluated. So the loss goes from near zero during training and then spikes all the way up to 7 times 10 to the 23rd. I am not entirely sure why that is. I believe it's probably poor configuration of the models, the data set being too small, or not enough training epochs being used. Furthermore, in addition to the loss curves looking almost identical for each of the user-defined models, I calculated the mean square error of a test split of the sample data. All four of the user-defined models were incredibly high. They were different so that I at least know that the models were being trained in a process that was specific to them. It wasn't just outputting the same number each time, but still they were incredibly high and almost identical. After training the user-defined models, a pre-trained model is imported, and the data being used as the drugs is the DEEPPURPOSE antiviral drug data set, and the targets, the disease proteins, are the user-defined diseases up at the top, these ones. After the user-defined models are trained, the antiviral and the historical diseases are loaded, and predictions are made for affinity scores using all of the user-trained models as well as the pre-trained model. Overall, the binding affinity predictions for the user-trained models are unrealistically optimistic. A binding affinity score close to zero is very good. It indicates a drug candidate that could have a potentially beneficial effect when interacting with the disease. And the further away you get from zero, the less predicted impact that drug would have on the disease. Um, However, with the user-defined models, uh, they all not only predicted binding affinities for the antiviral drug set and historical diseases close to zero, but the recurrent neural network model actually predicted binding affinities that were below zero, which shouldn't be possible, and is further indication that there was some misconfiguration of the user-defined models. The pre-trained model, on the other hand, performed very well. It showed a number of um, drugs with predicted binding affinities close to zero, and then a wide range up to uh, a maximum of approximately 35. Just to illustrate the comparisons of the user-trained models, those predicted affinity scores versus the pre-trained models' predicted affinity scores, a scatter plot was used. Again, because the predicted affinities of the user-defined models were so low, the scales of these charts appears way off. But each axis does show predicted affinity scores. Um, Overall, the user-defined models performed very poorly.